So we're going to talk about custom layers. I'm Yann Cabon. I'm lead developer on the API 4, especially on the 2D side, and I'm joined with Joe.
And I'm the lead developer on the 3D side in the Zurich R&D office.
Yeah. So today we're going to talk, so this is the agenda. We're going to do an introduction about the layers in 4. Then we're going to show a lot of code about implementing dynamic layer, a custom tile layer, how you can make like load resources before the layer starts to be displayed. Custom elevation. And then more advanced, even more advanced topic like using web workers, and then some of the future work that we're gonna tackle after Dev Summit. So the layers in 4 are different than the layers in 3. In the 3x API, a layer has the data to display and is also in charge of displaying it. In 4, we have separated that. We have on one side the layer that has, which is just a connection to a service or to some data. And then on the other side, we have the layer view that is capable of actually drawing. The layer view is more complicated to implement because it's 2D specific or WebGL specific, even in 2D or 3D. So you want to create you may want to create a custom layer for cases like if the API does not support yet some layers like a WMS, or if you want to connect to some services that we will likely not support. So you have like a service online and you just want to display its data. You may want also to create a custom layer if you want to process the data before being displayed. We're going to show some examples. It's going to be a lot of code actually today. And then you know, because you can if you want. So so we're going to cover like dynamic tile and elevation layer. Most of the code that we're going to show is going to be working in 4.4. So we started the working on those layers, but not ready yet. So custom dynamic layer. So the dynamic layer is a layer that displays a single image, actually 2 in the case of the SceneView, to cover the entire area of your map. So the user interacts, he pans around, and then he finishes the interaction. Now the layer view will issue a new request to get a new image, and then when that request succeeds, it will display it. What is nice about it is that you have like few exports. It's going to be done only at the end of an interaction. But then the problem is that this image, when it's generating a URL, this URL is most likely to be different every single time because the envelope, the bounded box, is different. So it cannot be cached in the browser.
One disadvantage on the 3D side is that because if we did only one image, then we would have only a single resolution. But if your view is tilted, the things that are close to you appear much larger than the ones in the back. So we actually need like a continuum of resolutions to create a nice picture. So that's why we do 2 requests, but that's not enough. So tiled layers are much better in that sense that we can have a much better sort of a ramp of resolution towards the back of the image.
Yep. So in 4.4 we'll introduce like at least 2 new classes. One is going to be base dynamic layer. That will be the equivalent for tile layer. The base dynamic layer you will. Whoa, I'm going too fast here. The base dynamic layer, you can implement a function called getImageURL. This is the easy way to implement it. So this function will be called with the accent of the view and then the size of the image that the layer needs to display. And then you can create the URL for this image. Then the layer view will fetch that image for you and then display it. The other way is also could be to implement fetch image, which is actually doing the entire process. It's more interesting if you want to process the data. If it's, for example, you fetch it's not directly an image, it can be binary data and you want to draw it on the screen, you need to do some rasterization on the client. So the default implementation of fetch image in the base dynamic layer is gonna call get image, get the URL, and then fetch that image and display it. So first example, so I'm from Brittany in France, and Brittany has a portal that that allows the citizen to access lots of different data, and all that data is mostly in WMS, can be accessed through WMS. So here is, for example, one of the scan, one of the base maps that you can find in France. Oh, okay. PowerPoint and Mac. Horrible. Yup. I'm gonna continue this way then. Yeah, so this is a Geo-Bretagne, and so it's an interface with, you can search for in the catalog of different services. So we're gonna see how I picked one of the services, which is actually the parcels, and then how to display it. So this would be the end result. So it's a WMS service that you see, I just stop panning and now it refreshes. And if I pan again, it will refresh. Right. Take some time. All right, yep. Let me close this. All those examples will be put on GitHub, but I need to do that this week. So this is the code of the app. So I created a custom WMS layer, and then I will declare two properties on my layer. One, which will be my WMS endpoint, and then the request parameters. So some of the request parameters for WMS, like we need to specify what type of request we are making, so get map to get the image, the version of WMS you are using, the layer we want to display, and then some parameters that the layer view will specify, like the width and height of the image, spatial reference, and the bounded box. Then I add that custom layer to my map and create the map view and so on. So this is how we would look like. So we will have that new base class, base dynamic layer. The name may change because all layers are kind of dynamic in the API, so we have to figure out a better name. I declare two properties, get map URL and get map parameter, and in this case I only override get image URL. So the get image URL will be called with an extent, the width and the height. What I do is that I serialize all the parameters that my user has passed, so like the request, the service WMS, and so on. Then, so I have this function here. Then I replace in my URL string in my get map, I create the query string, and then I return this URL. So that's mostly it. If we look at the this is all you have to do to create, to connect to a service. So yeah, this is the final. I don't know if we see very well. Up. Yeah, so the query string parameter here will change mostly like just the bounded box as I pan around. All right. So custom tile layer. So this layer basically is stitching together adjacent tile images that have the same size. Commonly, it's 512 by 256 by 256 pixels, or 512 by 512. The difference with the dynamic layer is that new tiles are requested as the user pans. What is really good about that is that those tiles are cacheable. They are always at the same place. So we just have a level row column, and it's possible to cache them in the web browser. It's also cached at the service level. The inconvenient is that, is not really one, but still to be an efficient layer, the service to deliver the tiles needs to deliver them really fast. So for the base tile layer, the extensibility hook will be to override either the get tile URL, so you get a level row column and then you need to generate a URL, or the fetch image, which actually it's not fetch image, it's fetch tile, which will have also the level row column, but then same, you can process the data before returning it. So I will use the same, I will use another WMS service on GeoBretagne and then display it with tiles instead. And I have, okay, so, all right, so this will be my final app. This is the scan, and then it's really interesting because they have also published some aerial picture from the 1950s. So my high school is somewhere here. It doesn't. Oh, come on, it's horrible. Thank you. Yeah, so very old like imagery. My high school is here, and there are many buildings around it. It's basically like full city now. And the other one is the scan. So I will be using a custom tile layer, and each request will be a custom WMS call. All right. So, all right. So this is my app. This is the app. All right. So I have a first layer with the imagery, same parameters, and then the scan, same parameters. Between the two, the only thing that changes is really just the layer that I will be asking. And then I create a group layer with those two layers, and then a map with that group. So, so this is how you would declare it. So you would extend base tile layer, declare your properties, and then in this example, I will override just the get tile URL. And then the layer has some public method to help you figuring out, for example, the extent of a tile, so get tile bounds, and then you can use those bounds to actually send that for your export. And the rest is exactly the same code. You could eventually create a layer that could both work in 2D, like in tiles or dynamic, depending on some options. All right, a different example. So to use, to override fetch tile. So in this case, I'm using a toner base map from Stamen. Normally, instead of being white, like purple, like here, it's white. The default style is white. So what I'm gonna do is fetch the tile and then draw it on the canvas and pre-multiply it with a purple color. So it's an easy way to customize quickly a base map without recooking the entire cache. All right. So the app is pretty simple. So here I have created a tint layer. I don't know if I'm saying it correctly. And then with ZXY parameters, I provide a color and then a title for my layer list. And then so the layer, I declare some properties like the URL template, and then a tint property, which is of type color. Here I'm overriding the get tile URL, where I take the URL template that the user provides, and then I replace it. I replace the tokens with the level row column. So I generate my final tile URL. And then in my fetch tile function, I call get tile URL, get my URL, use Esri request to request for the image. Then I get the response back. I have the width and height of my tile set, so it's 256 by 256. I'm creating a single canvas with a 2D context that I size to the size of my image. And then if I have a tint, I will set the style on my canvas context, fill the rectangle in purple in that case, and then I will ask for the next draw call to be multiplying the colors together. And then I draw the actual image data. I return that canvas as this is that canvas that is being drawn. So you have like a tile of canvases, basically, like a layer of tile canvases. All right, back. Loading and integration. So a layer, when you create it with a URL to an ArcGIS service, the layer is not operational right away. You need to, the layer needs to first fetch information on the service. You fetch the JSON metadata of the service, and then from that JSON, it will grab, for example, the full extent of the data, the information about the tile cache, and so on. It needs also to verify if the service exists actually, because that's maybe a URL that points to nothing. So grab the extent, title, attribution, and so on. So here I have an example showing this. So in this example, it's another use of Canvas to do something. So this is the Grand Canyon, and this is the world imagery. And what I want to do is to blend that imagery on top of the world hillshade service. So, and then what it would look like. So this is the regular imagery, and this is the one blended, right? So you get the relief is shaded, and much you can see much more details. It accentuates the details, kind of. All right. So I created a layer called blend layer. It's extending that base tile layer again, and then let's start with the app first. So this is how I create my blend layer. I pass it two layers to multiply together. One is going to be the world hillshade, and it's going to be blended with the world imagery layer. And then I give it a title. So we have a guide in the SDK to explain what is a loadable resource. This is what we're going to implement here. With the API, stable, yeah. So this page explains what is the status of a loadable object. So layer is a loadable object. By default, its status is not loaded. Then after, when the layer is added to the map, the view will call load on that layer to make sure that it has the appropriate information. So it's going to be in loading status, and then after it's going to be loaded or failed, depending of if the layer managed to fetch its resources. So there is a lot of information about the concept here. But in concretely, what's happening is that we will implement a load function, and then that load function needs to basically start the loading of all the resources needed for the layer to work. So in this case, I will go over my two layers to multiply. I will call load on it, and then I will call that a loadable function called add resolving promises. So a layer may have to load multiple resources before being ready. So we can add a lot of resolving promises, and then only when all of them are resolved, the layer will be functioning. So here I'm loading my two layers, this is returning a promise. I'm adding this one, and then I'm adding a fake one, like just a set timeout, and then 2 seconds after, I will resolve my promise, and I add this one too. So when those three promises will be resolved, now my layer is ready, and the view will start asking for tiles. It's only after that. All right, and then for the pre-multiplication, what I've done is the same. I override that fetch tile function, but instead of calling get tile URL, what I do is that I ask each of the layer that this layer contains to fetch the tile, and then when all the tiles are fetched, I take a canvas, I create a canvas, and then set the compositing of operation to multiply, and then I draw each image on top of each other. So like that, you have that loop. you have this shaded effect. It's pretty nice. Right, I'm done for now. All
right.
Yeah. I can go back to this.
Cool, thanks. So I'm going to talk about how to do the same thing essentially with elevation layers. Elevation layers are currently always tiled layers. They're pretty similar to what Yann has already done with the tiled map layers, but there are some subtle differences that are actually important if you wanna do it. So I'm going to talk about those. Well, the basics is exactly the same, like the basic mechanism of creating your custom elevation layer. There's another base class probably called base elevation layer, and in there you can override either fetch tile URL or get tile URL or fetch tile. Now in Yann's case, or let's say in the map layer case, what you have to return from the fetch tile call is an image, an HTML image or an HTML canvas. Those work the same. For elevation layers, you have to return, it's always a promise that you actually return that will resolve to an image. For the elevation layer, you will return a promise that resolves to this object here. So it's an object that contains 4 properties. The most important one is the values property, and that's an array that contains all of the elevation values in that tile. I'm going to talk about that in a little bit. And then the width, the height, and the no data value. I'm going to talk about that later as well. So here's the important, subtle but important difference between elevation and map images. When you think about a tile, and when you think about an image, in fact, like a typical way to think about it is it's a grid, and every cell of the grid has a color. And typically, like when you think about where does that color belong to, the best answer, if you need to give one simple answer, is to the center. It's not true, like there's all these like sampling of images and everything, but let's assume like that's the case. So for our color images, we have this grid, and the color represents to the color at the center of that cell. The get tile bounds, Yann has already talked about that, returns the boundary, so it returns the left side of the grid and the right side of the grid, or top and down. And then there's this value called resolution in the services for each level of detail in the tile pyramid, and that corresponds to the size of one of these cells in map coordinates. So if it essentially tells you, okay, 1 pixel at this level in the image is like, I don't know, 100 meters wide or 1 meter wide or 5 centimeters, something like that. Sorry, I'm European, so it's all of these metric values. And then, rows and columns is the number of pixels. As Yann has already said, that's typically 256. So that's the map image. That's what you need to return in terms of color. For elevation, the samples that you need to return are at the corners of the grid, not in the center. And this means that if you have 256 cells, you actually need to return 257 values, because the simple example here is that if you have 4 cells, then there's actually 5 corners in one dimension. And so you need to make sure that you compute the elevation values for those right locations, that it's the grid corners and not the centers, and you need to make sure that you return 257 by 257 values instead of 256 by 256. However, just a note, the tile info on the layer will still state that it has 256 values. So we just have this kind of duality that we say, okay, if our sort of tile kind of size that we want is 256 by 256, just in case that we return elevation values, it has to be 257 by 257 values because of that odd spacing as compared to the map image, the map tile layer. And one more consequence of that is that if you look at 2 adjacent tiles, there's actually 1 row of overlapping values. So in the terms of, for the color pixels, the cells, they connect to each other, but they don't overlap. In this case, for the elevation values, every tile, any tile border has an overlapping row between the 2 neighboring tiles. This is actually, the reasons why we do it that way is because it's much easier to render it that way. It's much faster, more efficient to display this kind of terrain data. So that's sort of the contract that you need to fulfill when you want to implement your own elevation layer. This is actually the same for 2D and 3D. Just one more note. The y coordinates are kind of upside down. So the map coordinates typically, or I think in our case always, grow from like south to north. So south is the smallest value, north is the largest one. Whereas the pixel coordinates, they always go top down. So the top row is the first row and then it goes down. So when you go from like map coordinates to pixel coordinates and back, you always have to like swap the y coordinate around. Okay, I'm going to show an example in a bit. I just want to say that if you're interested in more detail about how our elevation services work, there's this brand new document online that describes how you could consume the Esri elevation services, and that also explains all of these things again in more detail. Yeah, so now I have some examples.
You want to show this one or no?
Oh, no, I guess it's fine. Yeah, you can just click on the link when you get the slides. So here's a fun example. That's just really toying around with that concept. But what I've done here is I've created a custom elevation layer. We can take a look at what it does. So it looks the same, as I said, to the samples that Yann has already done. I'm creating a subclass of the base elevation layer. Is it big enough? Maybe a bit bigger. Yeah, here we go. And then I define some properties. In this case, this is kind of overlapping sine waves. So I define a frequency and a magnitude. You can see that the magnitude here is 1.5 kilometers. No, sorry, 1,500 kilometers actually. That's why it generates these tiny bumps. And I'm overriding only the fetch tile method because I'm essentially creating synthetic elevation data here. I don't fetch any data. So I just override fetch tile directly. I get the level, row, and column. I compute the bounds of that tile. I get the number of cells that I need to produce from the tile info. And then, this is what I said before, the number of elevation samples that I need to emit now is that value plus 1. Root size is just the size of the entire, essentially the Earth's circumference in this case, so it's size of the tile at level 0. And then I compute the size of one cell at the current level, so at the level that we're given here. Create an array, and then I go through for each sample that I need to return, I essentially compute these two sine waves. And then finally I multiply the two sine waves together with the magnitude, store this in my resulting values array, and then here is where I return this is the return value of the fetch tile, and you can see I have the values, the width, the height, and no data value. I'll talk about that in a bit. So, and that makes the scene viewer actually consume these values as elevation data and show them.
No use case for it.
No use case for it, absolutely. That's just pure fun. Maybe you can think of one. That would be cool. But okay, so here's a more serious example. It's perhaps not the best one because this is really a feature that we want in the platform. We just don't have it just yet, so we're working on it. But it's an easy example to make of a more useful use case. So obviously, this is elevation exaggeration. We fetch the data from the Esri elevation service, and then just multiply it with a certain number, and then give it back. So let's take a look at that one. Starts out a bit differently. So I override the base elevation service. There's a URL template that points to the world elevation service. And then I can define a factor. This is the amount of the exaggeration. Get tile URL that just instruments the URL template. And then here's fetch tile. So here I first fetch the elevation data from the Esri elevation service. And then I decode it. Actually, I should bring that up as well. So the one component of the Esri elevation service is a compression format for elevation data, or for raster data in general, sorry. And this is called LERC, and that's the format that we use for our elevation services. And so this is on GitHub. This is public specification, including source code to consume that, to decode it. Yeah.
Can you show the LERC decode?
In here, so yeah, the JavaScript implementation is.
Other languages, yeah.
Oh, thank you. Somebody's already used it. Awesome. So here's a LERC decode. This is a JavaScript decoder for that. So if you want to use, like, get the values, you can use that directly. I've actually.
This is what you use?
Yeah, I'm using it right here. You can see. Yeah, but where is it included? Oh, then it's, yeah. So by some like module import magic, I'm fetching it directly from GitHub. And then in here in the fetch tile method, so I fetch the raw data from the service, then I call decode on that. So what I get back is now just an array of the elevation values. Basically what I would need to return down here. But now I'm going in and multiplying each value by the given factor. And so here's one more like stepping stone, this ominous no data value. We have support for this elevation services can have certain pixels where we say there's no data here. We don't know what it is. I think typically that happens when like over water bodies or so, where the returns don't match. And so you need to be aware of that. Whenever you fetch a tile, when you use this LERC decode here, you can actually pass in a specific value that you say, okay, in my array of elevation values that I get back, any pixel that you don't have, just put this value in. So then later I know what this is. And this value is actually given to me by the API. So we essentially, when you override fetch tile, the API tells you put this value in all the places where you have no data. And so I'm passing this here back into the LERC decoder, and then I'm passing it back in the result. And yeah, that's elevation exaggeration. That's it for elevation.
All right. Yeah, can you put me back?
Yep.
So actually oops, okay, again. Right, so I did also a layer for 2D for this called LERC layer that display the elevation, but drawn rasterized on the canvas, so in the like a shade of blue, so the higher, like the bluer is the higher elevation. So to do this, again, pretty simple. We call, in the fetch tile, I do the same. I call a Esri request to fetch the elevation data, and then I call decode. But the big difference here is that I'm doing the drawing myself, so I iterate over the data and then put the data back on the image. I think there is an example already online for this. All right. So this is our last set of examples. It's going to be slightly more advanced using web workers. So web workers are basically light threads that runs that you can use in the web browser. So it's very interesting if you want to execute expensive work on data crunching, for example, and then the problem is that if you execute that in JavaScript, you may block the main thread, so then the user cannot interact anymore with your map or do anything while the code is being executed. So the idea is like, oh, I create that web worker, I tell it to do something, and then my app in general stays interactive during that time. Then I get the result back, and and then I do something with the result that worker gives me back. Okay, let me quit this. So we introduced in 4.2 Esri Coworkers. We have created a framework inside the API when we revamped the implementation of the vector tile layer. So we created Esri Coworkers. It's a layer on top of the Web Workers API that exists in the web browser. What we wanted is to be able to load any modules, AMD modules inside the Web Worker easily, because it's setting up Web Workers can be kind of a pain. So it's kind of an RPC framework. You ask you ask the framework to load a module. We call that open a connection, and then when that connection is open, you can invoke method inside the object, inside the module that is created in the worker, and then the worker work, and then it resolves his, it finishes his work, and then you get back the result. So there is a diagram here. Let me try to make it bigger. There is a diagram here kind of detailing the workflow. So we call here worker.open, and then when the worker framework initializes itself, loads Dojo loader actually inside the worker, then loads the module, then says, okay, I'm ready to work. Now in the second step, we tell it to invoke the method and with parameters. Then the method is executed in a worker, and then when it finishes, your promise in the main thread resolves. So, like a month ago, the creator of Leaflet, Mike Bostock, he tweeted about a blog article explaining how contour lines were created, like one way of creating contour lines. I'm not really familiar with the other ways. Let me refresh that. But it was really interesting because the blog post explains how interactively how to generate contour lines. So if you have like elevation data like this, you divide, you sample the data, you sample multiple points, and then you divide your area into many triangles, and you compare the values at each vertices of your triangle, so to see if the triangle, what is the orientation, and then you generate segments of lines, and then you concatenate all the segments, and you have your elevation. And then he explains, like, he details in code, it's in Python, everything that he did. So I was like, okay, that sounds pretty doable. And so I came up with a layer that actually consumes the elevation data from the elevation service. Since we have, in that binary blob, we have like each individual elevation, correct elevation there. And then this is displaying one ISO line. So I will go over the code, but then the problem here is that this is working in the main thread. The problem with that is that if I try to generate 80 ISO lines like every 100 meters, it's gonna stall. So I use the web workers to create that. So here it doesn't show a lot of them. It's like 8 ISO lines, one every 8,000 meters. But then I can easily like go to my app. And then let's say I want to generate an ISO line every 100 meters. And you're gonna see that my machine maybe may do some more noise because there is quite some work to do, but it stays like completely fluid for the user. I don't know if it's intelligent to do those kind of stuff, but it was interesting as an exercise. So, all right. So I will go over the code that is not working in workers yet to explain a little bit how it's working. So I created that contour layer. It's a tile layer, so it's handy because like that once the ISO lines are created, the contour lines are created for one tile, I can just move around that image without having to recompute them. So I have a URL template pointing to the world elevation, and then I created my get tile URL, and this is the meat here. We have fetch tile, which requests the elevation data as an array buffer, and then creates a canvas, decode the lurk data, and then I say, okay, I want to draw my line in red, and then I have my function, which is kind of it's a part of the algorithm that was detailed in the blog post. So I won't go in detail, but the different steps are to divide your tile into many triangles, and then for each triangle you will create the segments. So you will see if there is, if the elevation, if one of the vertices is crossing one of the thresholds, so let's say 1,000 meters, and if that's the case, we compute what is the segment between the two the vertices. So this is the algorithm. Then once I have all my segment, you want to rebuild the final lines. So it's a lot of code for, in the end, just getting the lines. And then in the end, I return my canvas. So now, to make it happen inside the worker, this is how we combine kind of everything that we showed before. In the load, when the layer will be loading, this is where I will start my connection to my worker. So I will ask, I will get what is the module that I want to load. So the algorithm that I just showed, I created something called contour worker. This is just an object that has like a function called generate contour. So this is this one that I want to call from my main thread. And then it has the same function here. So I lost my file. Worker layers. So then I open the connection to that module, and then when it's done, I set that as a private property of my layer, and I add the promise to open the worker in case of like I don't know, the module does not exist. Then the layer will fail to load. But if I manage to open the connection, then my layer will be loaded. So I call getTileURL, and then the fetch tile now is going to be a bit different. So first I request the elevation data, but then instead of drawing it directly, I will invoke my generate contour inside the web worker, and I'm passing the lurk data directly, so not even decoded, so it's still binary. Some info, so this is some configuration. This is where elevation is like an array of objects that describes what are the contour lines I want to generate. So if I want to have 80 contour lines, I will just like say I want a contour line at this elevation and this elevation and this elevation. And what is the size of my data? And then this returns a promise. So I return this promise, and then in the next step, the worker has worked, and it gives me back something, right? Some result, and then I create my canvas, and then I will go over all my different elevations that I want to draw, and draw the contour line from the result. So that result object is basically all the different lines the points that I need to draw. So this is how I draw. I go over all the contour lines that I want to generate. Then I start to draw a line. So I move to the first point in the line, and then line to the next point, and so on. And then yeah, that's basically it. Yeah. So.
One thing, by the way, that we forgot to mention is that since we're only operating at the layer level at this time, this works exactly the same for MapView and SceneView. All of the layers that Yann has just showed you in 2D, you could just plug a SceneView to it and it would work out of the box. Obviously, the elevation layer samples that I've shown, they only work in the SceneView because the MapView doesn't consume any elevation layers, unless it's done the way that Yann has done it, kind of turning it into a map layer. Yeah.
So as a future work, this is kind of what we are looking at right now. We want to build some useful examples. So one could be to load a TPK, so tile package file, if you want to consume it offline. Drawing vector data. Drawing vector data, so have some examples to consume features and then draw them. And then we would like to know also what use case do you have and what you would like to see as examples or as capabilities that we would need to think about to integrate that into those base classes. We need to see also how to refresh the data. Right now, if we change some properties on the layer, we don't update the tile. So this is the kind of stuff. And then custom layer views also, if we want, one of the usage would be if you want to animate the data on the canvas, like how we would do that. So.
Yeah, so on the layer views part, I can show one thing. This is kind of just a little bit of a plug. For one thing that I mentioned in the plenary is that if you really have a specific visualization need in 3D, like in 2D, you can do exactly the same. You can just go ahead and directly render that on the screen, right? In 3D, it's a bit more complicated, and you actually have to do WebGL rendering and everything. But if you go to the JavaScript API, search in the reference for external renders. It'll talk about how to do that. So you can kind of create your own visualization. Here's an example of that. Unfortunately, there doesn't seem to be a lot of wind in Redlands at the moment, so it's moving slowly. But this is an example of an animated visualization that we don't support out of the box in the... Pardon me? Yeah, the shadow doesn't move. That I actually noticed that when I call it up before, because the shadow is actually a part of the image layer and not of the visualization. I could now probably, to confuse you, turn on our shadows as well, and then you have two shadows and one moves and the other doesn't.
These samples consume real data about the windmill here next to Palm Springs. So it's pretty nice. Like it's a model that is animated in JavaScript, but it's real data. So if it's very windy, they would
spin.
They would spin.
Yeah, and this is an API sample you can find in here as well. It's probably linked to from this page. And if you're interested in that kind of stuff, if you already done some WebGL stuff, there's a demo theater tomorrow at 2:30 by Esri, where he explains how he did that wind visualization app that you've seen in the plenary.
Yeah, some very, very interesting usage of 3D there. It's pretty nice. All right, and we'll take some questions if you have. Yeah, thank you. We killed everyone.
Yeah. It was fast-paced, actually. Sorry about that.
Yes. So the 2D demos, they are available. All this code is available on GitHub. Oh, sorry. Can you switch me back?
Oh yeah. Sorry.
Up. In presentations. Right, and then it's, over here. I don't know if you see. But, you will have the link to the demos inside the slides also when they will be available in the proceedings.
Question back there.
Sorry?
Are there any performance considerations in terms of the size of the data that you send to the
Yeah, there are some, I don't have the definitive answers. There are some, so in the case of Lurk, it's a binary array buffer, so we can transfer it. So it's by default, when you send data to the worker, it's going to be copied over. So if you have a gigantic array of numbers, it's going to be copied, and this takes some time. But if you have that inside an array buffer, you can transfer it So as soon as it's transferred, it's not available anymore in the main thread. And then after, you can process it there and transfer it back to the main thread. And it's quite fast. What you can do also is if you have like large JSON objects, you stringify them, and it's much better than sending the actual object. Yeah, no, it's okay. I mean, the vector tile layer is using a lot of array buffers, and it's fairly fast. Yeah. What is nice about the worker framework is that we are just like consuming any AMD module. So your module you can make it work in the main thread if like main thread or in the worker seamlessly is the same way. It's good. Yeah.
Do you mean requiring Dojo and the JavaScript API in your worker?
Yeah. We load the Dojo module inside the web worker. Yeah. If you are using the API with require.js, it's still gonna be the Dojo loader that's gonna be loaded. So in the documentation, I haven't talked about that. Sorry, let me show the. Let me find the example. One of the things you have to do when you are using the worker framework is that you have to configure. So on the main thread, you configure your Dojo config or require.js the way you want. But then, since it's the Dojo loader, you need to configure a specific object called loader config, which is kind of it's a Dojo config if you want, but specific for the worker. So here I'm specifying the path to like the lurk module, for example. So yeah. All right.
Yeah. Thanks for coming.
Thanks. Have fun.